Okay, so up to this point, we've been talking about position time graphs, we've been talking about velocity time graphs. One thing that we had to deal with position time graphs was that idea of tangents, like when the graph is curved, right? And that's a little bit of a hassle because we have to deal with tangents and maybe multiple tangents in order to gather velocity time information. But this one's a little bit different. This is the idea of a curvy velocity time graph. And I haven't even been nice about it. It's not even like a quadratic or anything. It's like this wiggly, waggly thing. I want to propose that we can handle this. And the idea that allows us to handle it is actually something that goes back to, believe it or not, ancient Asian land claims. Weird. So if you've ever looked at I know, right? It turns out that if you've ever looked at any land mass that has a wiggly shape, can you imagine that this is like a farm territory that's bound by rivers? Everybody's seen like the rivers of China. Like there's like huge rivers. Makes sense. This could be farmland. But then, like any empire, doesn't the emperor want to tax the people? Taxes. It all goes back to taxes. And so having a weird property shape like this is tricky if you want to figure out how to tax people. It's also tricky if you want to approximate what the food yield is going to be off of that property, right? Like we all know that you could figure you can get so much wheat off of so many acres per year, or so much rice off of so many acres per year, or whatever it is. This is something that has real economic value. It's not just that I want to like lean on the Chinese for some reason to get some ancient knowledge or whatever. I want to say, hey, people had a great idea here. And the great idea goes like this. We take our strange shaped land, and you'll want to have a clear ruler for this, like so often. And I want my stripes to be drawn in equal thicknesses. And if this was a single farm, and somebody wanted to figure out how much acreage this farm was, what we're talking about is finding the area of a curved shape. Now, I get that in math class we might talk about functions, and this isn't truly a function. This is a shape. But now I've got my land sliced up. And you might literally run straight fences through the land to do this, or if you have good map makers in your society, you draw a scale map and you do exactly like what we're doing, right? So I mean, that's a matter of where your cartography skills are at, I suppose. But we're going to slice this up into strips of land. Now around here, colonial North America, I think if you've ever seen colonial maps, you know that the land was divvied up in rectangular strips because it was easy to do at the time when you were carving up a territory, but also it was nice for making roads that are straight in between farms, but also it was easy for calculating the surface area for crop yields and things like that. And also it was easy for taxation purposes for acreage. Like there's so many reasons why if you were starting to divvy up land from scratch, and I know that the land was taken from somebody who owned it before, but if you were going to erase all that and start new with land ownership, rectangles make sense. But if you're talking about a society that's had properties in the family for quite some time, and you're going to go back and figure out how the land area works, this makes a lot of sense. Now there's a whole branch of math, and I'm going to get the pronunciation wrong, Henry mathematics, and there's a reference to it in the worksheets. I actually think that might be a Japanese word, but I mean, I'm still going to mess up the pronunciation. You can look it up. It is referenced in the worksheet. You can see it there if you like. But this is the way it works. It's actually the beginnings of calculus. It's a pre-calculus, and historically it came way before Newton's version of calculus, okay? So that's kind of a neat thing that this was figured out way before Newton. And it goes like this. Just like there is this seductive dance of the tangent, this one is a very careful one as well, okay? What I want to point out before I even draw a line, can you see that my ruler for this first strip, can you see there's a little triangle above the ruler and a little triangle below the ruler? And if I was going to think about rotating the triangle above the ruler, can you see that it would be the same area as the triangle below the ruler? That's my goal. I'm trying to make the triangle right there and the triangle right there be the same area. I'll color them in just a second, okay? Boom. Oh, I did a bad job. I'll do better on the next one. So my idea here is that I want, if I was going to think about rotating the triangle above the ruler and a little triangle below the ruler, this triangle below to be equal in size to the triangle above. I'll do it better on the bottom. Again, I'm going to draw a horizontal line. And see this triangle right here? It's the same area as that triangle right there. And what I've effectively done is I've made a rectangle. Now the rectangle has area, but because I added an extra triangle in this little wedge and neglected a little triangle that's the same area up above that rectangle, the area of that rectangle is now the same area as the weird blobby shape that was cut through it. We'll do it again. I'll show you what I mean again, okay? Again, I take my horizontal line, and maybe this one will be easier to see. I'm saying that this orange triangle, and I don't know if I have another color, this pink triangle, maybe that's easier to see, are the same area. And the bottom of this curve happens to be more or less flat. So I'll just draw a line straight through. Then I do it up here, maybe this will be even easier to see. Draw a line here. Again, the area that's inside of the rectangle and the area that I'm ignoring outside of the rectangle are about the same size. And so again, the area of this rectangle, oh, it's more or less flat on the bottom again, that's lucky. But the area of the rectangle is approximately the same size as the area of the weird shape that used to be bound inside of this strip. Does that kind of make sense to people? This is an approximation method, kind of like the area version of a tangent. It's an approximation method for sure. We're trying to find the area of weird curved shapes. And I'll just go quickly, I'll finish this off. Just keep on going. Each time I draw a horizontal line, I'm trying to neglect the same amount of space as I'm including. And it's really most noticeable when the line is slanty the most. And this one that I did near the end, see how I'm neglecting this triangle, but including this triangle inside the rectangle. Effectively, what I would go back and do is I would go back and I would measure the widths. And if I'm being good about this, all the widths should be the same value, all the way across. The width of every strip should be the same. But what would be different for every strip would be the lengths. So I would measure the length of each strip. And that length times width measurement could be done for every single strip, and then the area of each of those mini rectangles could be added up to be the total acreage for this oddly shaped farm. And whether it's for crop yields or for taxes, now I know how big the farm is at least, right? And so it makes sense that people would want to do this. Now the original, formal math drawings for this actually show this using circles. And interestingly, if you're really careful about this with a circle, and you can go and see if you can find some documentation for this online, but if you're really careful about doing what we just did, but for a circle, it turns out you can find the area of that circle, and you could relate the area of that circle to the radius of that circle, and you could use this method to prove the value of pi. That's wild. I mean, we would use pi r squared as the formula, right? That would be a neat, different way to prove the area of pi. Not a way that we teach in our classrooms, because we teach the Greek way. This would be the Chinese, or I can't remember if this was originally Chinese or Japanese school of thought, because there was overlapping schools of thought. But this would be the school of thought from that part of the world, right? And I think that that's kind of a cool thing to see that people call this ethnomathematics. It's neat to see that different ideas can can arise from different ways of thinking, right? And I love that. But in this case, that way of thinking fits better with graphs. And so when I come over to this velocity time graph, now I don't know, because I didn't meet the fellow. I don't know if Newton had this kind of thinking in mind when he was determining his, or Leibniz, approach to finding the area under curves using calculus. But as a pre-calculus approach, this is a great way for finding the area under a curve, at least an approximation method way. We would make equal width strips, and just like the property calculation, property area calculation, we don't have to deal with a lower bound because this is a function, right? We just have to deal with the upper side of the property because the lower side of the property is a straight line. It's the time axis. And we can just go through and draw horizontal lines. It gets tricky when there's a hump in the middle. And it actually turns out that this method works best if the width of our strips approaches 0. The math people would call that in the limit, where the width of the strip approaches 0. This method becomes more and more accurate. It's really a question, if we're going to do it by this method, it's a question of what you have the patience for and how important the accuracy is. But I've done my best there as a human to make sure that the amount that I neglect above the line and the amount that I include below the line is the same amount, so that the area of that rectangle, for this one for example, would be the same area as underneath of the curve. That's the game plan, that's the goal, right? So we'll just make like a quick little statement here. We'll say finding the area or areas of the rectangles created approximates the area under the curve. And then specifically, since this is a velocity time graph, what quantity would I find if I calculated all these areas and added them up? What would I've calculated? Yeah? Displacement, yeah. So I could say, in this case, displacement. And I say in this case because it's a velocity time graph. And you recall, if I have a velocity time graph, I could say for a VT graph, we could think of a rectangle and a triangle even. Hey, look, if it was more complicated than VT graphs maybe we've seen in the past, can you imagine that a velocity time graph that looks like this, where it starts at a non-zero velocity and goes upwards, could be broken up into a rectangle and a triangle? But if it's curvy, boy, the only tool we have at our disposal is this old-fashioned method. And it's a great old-fashioned method. Never want to throw out the old-fashioned stuff just because calculus comes along. And like I said, we're talking about calculating the areas using the width of individual strips. And we could call it the length or we could call it the height. It doesn't matter. I'm just going to be consistent and call it the length of those strips. Okay? And then summing up all those areas. Okay? And we're going to go and we're going to do an activity, but before we do that, I want to take a look at the graphs down below. And I want to make sure that we can make sense of these graphs. All four of these graphs are position time graphs, and they all could be interpreted as a story. In fact, any graph could be interpreted as a story because you're really like graphically trying to explain data. So I want to just make sure these are sketches, so we'll call them position time the whole way across. The headers do that anyway, but I'll just to make sure that we don't miss that. These are position time graphs. And I want to talk about what's going on with these. Here, I'll do the first one, and then I'm going to ask for a little bit of help with the other ones, okay? So when I look at this, the slope is constant. If I think about rise and I think about run, the slope is completely constant the whole time. And so that means, well, what does that mean about the velocity? Does it change or is it the same?
Uniform.
Uniform, it's the same. We could say that it's constant. We could say that it's a positive slope, so we could call it constant positive velocity. I'll just use the symbol for velocity. I've said that it's straight, but the fact that it's not curved, which is the same thing as saying it's straight, but the fact that it's not curved tells you what about the acceleration? Is it accelerating? not accelerating. We could say the acceleration is 0, right? So I could throw in as almost redundant information, I guess it is redundant, 0 acceleration. Or I could say acceleration is equal to 0. Here's a question. Does it travel in the positive direction or the negative direction? Positive. Travels in the positive direction. I'm just making little notes about what I can see from this graph. Because I don't know anything about the story. And if I was going to come up with a story, if I said, hey, I would like this to be about a car, what's this car doing? Is there anybody that I haven't heard from yet? Somebody who's willing to tell me, what is this car doing? Yeah?
Accelerating positively.
It's not accelerating positively. Accelerating, it's got a 0 acceleration. What's it doing? Yes, sir? It's just driving. Yeah, it is driving. It's actually driving, let's just say forward. It's driving forward. Is its speed changing? No, it's just drive. What about where did it start? Did it start, let's just say that home is the origin. Did it start at home? No. How about we be bold about this? Let's just claim that the positive direction is north. I think we could make the claim that this car started at a position a little north of home, okay, and drove towards the north at a constant speed, okay? Started, let's say a car started at a position north of home and drove at a constant speed north. My gosh, there's a lot to say. Constant speed. I didn't mean to overflow my box there. But I want to give you folks, can I give you like a minute or so? Could you please think about this? What's happening with the velocity? So I'll label this up. What's happening with the acceleration? What's happening to with the direction of travel? And then could you please frame this as a car story? Okay? Well, I'm going to stop my recording for a minute. We're going to come back and we're going to take this up. But I want to give you folks like 8 minutes just to hash out what those rows would look like, okay? You don't have to keep the rows uniform because some of them are going to take up more space than others. Just answer those 4 things for each of these 3 little mini graphs, okay? Your time, guys. I'll put 8 minutes on the clock. Go.